This is the demonstration video of the TSN-based process automation system co-developed by Nestfield Limited and Hanyang University. Ethernet technology has proven incredibly successful and is a near ubiquitous method of communication in the IT world. Up until now, the standard Ethernet system still cannot satisfy the real-time requirements due to the randomized media access and the best effort forwarding mechanism. However, in modern industrial automation, robust determinism and RT performance are mandatory for process control and manufacturing systems. Therefore, the IEEE 802.1 task group is attempting to enable RT and deterministic capabilities for Ethernet via a set of enhanced standards, namely Time-Sensitive Networking, TSN. The primary benefits of TSN are to provide deterministic and real-time services, including guaranteeing the bounded latency, low jitter, and zero congestion loss for various time-critical scenarios. As an IEEE compliant, vendor-independent, and interoperable communication technology, it is the cornerstone for many industrial IoT applications in manufacturing. Due to the lower cost and ease of use, TSN networks can easily be scaled and integrated using a desired combination of other high-layer communication technology. For example, OPC UA. With these benefits, TSN plays a key role to implement Industry 4.0, and meanwhile, facilitating the integration of information technology and operational technology for industrial IoT. Moreover, TSN is not only applied to the industrial domain, but is also predominant for other disciplines that require hard RT communication, such as aerospace, smart grids, and intelligent vehicles. In terms of different objectives, the published 13 TSN standards can be categorized into 4 groups, including time synchronization, ultra-reliability, bounded latency, and resource management. We implement our TSN demo system by adopting 5 TSN standards. Adopt IEEE 802.1 A's to maintain the high-precision time synchronization among all TSN devices. Adopt IEEE 802.1 QBV to schedule TSN traffic so as to achieve the goal of bounded latency. Adopt IEEE 802.1 QAT and IEEE 802.1 QCC to establish the centralized network and distributed system architecture. Adopt IEEE 802.1 QCP to implement Young Data Model for the TSN configurations. The TSN-based process automation system has a 3-layer architecture, including cloud layer, communication layer, and field layer from top to bottom. The cloud layer provides a web-based human-machine interface to demonstrate and operate the entire TSN-based process automation system. The communication layer is a middleware that employs Automation ML and OPC UA aggregation server to connect cloud with field layer. By adopting OPC UA TSN, the communication layer provides real-time service to exchange robot control commands and status feedback with TSN end stations. The field layer contains various industrial facilities, for example, TSN switches, TSN end stations, Linux PC, industrial robots, and turntable for TSN-based robot control and turntable operation. The central network configuration is responsible for TSN schedule computation and configuration. In our demonstration, the CNC computes the TSN schedules for robot control and turntable operation. Through RESTconf, and netconf young, the TSN schedules are configured to TSN switches and end stations, respectively. The TSN switch performs traffic scheduling and switching functions according to a TSN schedule. Here, it is responsible for switching the scheduled streams generated for robot and turntable control, and the unscheduled streams generated for video display. The TSN talker transmits scheduled TSN streams for robot and turntable control. Once the talker receives the status feedback from controllers or sensors, the talker will forward it to the cloud through OPC UA TSN. While receiving the corresponding TSN streams from talker, the TSN listener also provides frame type conversion service, such as tagging or removing VLAN for the robot controller. The TSN module acts as a TSN agent to provide TSN services including traffic scheduling and time synchronization for the PLC controller to operate the turntable. Both scheduled and unscheduled traffic share a single link between TSN switches. We use open source software to run the traffic generator on the Linux PC and generate a massive amount of interference traffic to be handled by the traffic receiver, thus establishing a high load scenario. We use a media player to perform a video server and player, in which the video server sends unscheduled video streams to the player. The quality of the video depends on the available bandwidth of the shared link between two TSN switches. Under the high load scenario, the video quality cannot be guaranteed since there is extremely limited bandwidth available for the unscheduled traffic of video display. However, TSN always reserves sufficient bandwidth for scheduled traffic for robot control. Therefore, by comparing the QoS of scheduled traffic of robot control and unscheduled traffic of video display, we can show the real-time performance of TSN. This is the real-world implementation of TSN-based process automation system. The TSN-based process automation system contains 3 type-independent industrial robots: Epson C4 robot, Epson SCARA robot, and KUKA R540 robot, and 1 turntable. The turntable conveys an iron plate, and 2 robots execute the pick and place task successfully on the turntable. The monitor is connected to the video player and displays the live video sent from the video server. Now, we will show the real-world hardware implementation. The 3-layer device cabinet contains all TSN devices. The top layer shows that we adopt LS1028 board as TSN end stations and AML OPC UA TSN platform. The middle layer shows that we adopt Cisco IE4000 as TSN switches. The bottom layer shows that we adopt Intel Mini Nuke PC to execute the applications of HMI, CNC, traffic generator receiver, and video server player. The web UI demonstrates and operates the entire TSN-based process automation system. A table of TSN traffic includes source, destination, period, and delay constraints, and they are shown at the top. Below the table, it shows a static TSN topology that exactly matches the real-world field facilities. The middle graph shows the real-time bandwidth utilization rate of the shared link between TSN switches. At the bottom, 2 tabs are shown, namely TSN mode and Ethernet mode, which are used to deploy TSN or Ethernet configurations for the field network. At the bottom left, the button Traffic Generator is used to start or stop running the traffic generator. Under the TSN mode, we show 2 scenarios of low load and high load traffic by turning the traffic generator on and off. First, we show the low load scenario. The traffic generator is turned off by default. The shared link between two TSN switches has enough bandwidth, so the polyline remains almost 0%. The video can be displayed smoothly, since enough bandwidth is available for the unscheduled traffic. 3 industrial robots and 1 turntable can be well controlled. Second, we show the high load scenario. Click the Start button to turn on the traffic generator. The polyline reaching 100%, indicating that the interface traffic generated by traffic generator has fully utilized the bandwidth. Under this, the high load scenario. Video is frozen, since there is insufficient bandwidth for unscheduled traffic. However, 3 industrial robots and 1 turntable can still be controlled appropriately. This is because sufficient dedicated bandwidth is reserved for the scheduled traffic to control robot and turntable. The 2 operation scenarios verify that the developed TSN system can satisfy real-time requirements and is robust enough even under the high-load traffic scenario.